All right, so let's talk about the formation of the solar system. All right, so it's kind of a long story, but really the big driving factor of all this formation is gravity. It always comes back to gravity. So you'll hear me talk about it quite a bit. It's referred to as the architect of the heavens. So the universe is thought to have existed for about 10 billion years before our solar system, the Milky Way, even began to form. So during that 10 billion years, it's not like nothing happened. There was some accumulation of material. Really light elements were actually here from the very start. The Big Bang itself generated enough energy to fuse particles together to get hydrogen and helium, and then possibly even lithium and beryllium. Anything with mass has an attractive force to another thing with mass. And so we call that attractive force gravity. So gravity causes atoms of elements to clump together as a result. So these elements that were existing right off the bat started to come together. More mass means a stronger gravitational pull. So as this material started to clump together, they pulled in even more material. And so you can kind of see it as a snowball effect. Gravity squeezes these light elements together, which will raise the temperature as a result, because one of the principles of science is that as pressure increases, temperature goes right along with it. And if you get it hot enough, and I'm talking hot, fusion can happen. And what fusion is elements literally fusing their nuclei together to form heavier elements. When fusion starts to occur, we say that a star is born. In very large stars, hydrogen fuses into helium, helium fuses together to form beryllium, beryllium fuses together to form carbon, and carbon can fuse together to eventually form oxygen. This keeps going and going and going until kind of a critical moment when iron is formed, and that's when some different things come into play, like supernova. But this is the concept that you can see where, two heliums, for example, come together under high temperature and pressure situations, fusing their two nuclei together to form a new nucleus with 4 protons, which happens to be beryllium. And you can see how it's repeated over and over and how these different elements are formed. All right, so that's how elements were formed in the periodic table. It says after 10 billion years of stars being born and dying, the universe would have been filled with clouds of dust and gas made up of the 88 naturally occurring elements. So we've got the material out there. So let's talk about our solar system specifically. So 4.5 billion years ago, the universe would have been occupied by galaxies that were full of these clouds of dust and gas, which we call nebula. Within those clouds of dust and gas are molecular clouds. And these are special places where the material is just a little colder, a little more dense, and that's a really good spot for star formation to occur. Something happened to get those molecular clouds to start spinning. A couple different possibilities include a supernova explosion, very likely, or 2 molecular clouds just bumping into each other and setting off the spinning. Gravity is going to work in squeezing and condensing matter, raising the temperature, like we said. But because it's squeezing that matter, it's decreasing the size. And when you decrease the size of something, you increase the speed of rotation. Click this link here. So you notice when she pulled her arms in there, her speed of rotation increased dramatically. So that's what we mean by that. So the spinning material begins to flatten into a disc with a bulge in the middle. And that's actually a pretty complex reason why that is. And for our purposes here in credit recovery, I'm gonna skip that. But here's the shape we're kind of getting as a result. So I'm skipping that. Gravity continues to squeeze the bulge in the middle, making it hotter and hotter, and eventually we'll reach that critical temperature of 10 million Kelvin. And that's when fusion begins, and we have a star that's born. And in our case, we have our sun. So this is kind of a nice slide here that kind of goes through that chain of events here. So we've got the Big Bang Theory, where energy was turned into matter roughly 14.5 billion years ago. Our evidence for that include cosmic background radiation, or CBR, and the redshift. Stars start to form and turn the hydrogen and helium into even heavier elements. Stars do eventually die, usually around that critical time when iron is formed, sending heavier elements into space where they collect into gas clouds. And I know you're wondering, well, what about heavier elements than iron? How are those formed? That is kind of a separate lesson, but supernova explosions can get those elements to form. Okay, a cloud of these elements gathers, slowly starts to spin and flattens out, and the sun and our planets are formed 4.5 billion years ago. So that kind of gives you an idea of the timeline. And so we're going to talk about inner planets and outer planets to follow up here. Sorry, I'm kind of skipping ahead. So our planets. Planets are formed through a very similar process that we've been talking about, but we're going to use the word accretion. Accretion is the process of growth or increase, typically by the gradual accumulation of additional layers of matter. So gravity collects small pieces of dust together, and because there's more mass as a result, they attract even more matter. So kind of like what we talked about before, where we get this snowball effect that eventually led to our planet formation. What you need to know for sure, and some of you might remember this from like middle school, is the order of our planets. So we've got the closest one to the sun, Mercury, and we go to Venus, Earth, and Mars. That comprises our 4 inner planets. We've got the asteroid belt, or the frost line. Those are synonymous, separating our inner and outer planets. And then we go Jupiter, Saturn, Uranus, and Neptune. Don't worry about some of these other items like the Kepler belt, or I'm saying that wrong. Like, don't even ask me how to say that, sorry. Pluto was scratched off the list of official planets, so don't worry about him. And any other, moons and such, we're not interested in. Just the 8 planets with 4 inner, 4 outer. The reason they're so different, the inner and outer planets, is really just because of temperature differences. So within the frost line, rocks and metals are able to condense, whereas hydrogen compounds stay gaseous. And that's going to have an impact on their atmospheres. Beyond or outside the frost line, hydrogen compounds, rocks, and metals are all able to condense. So you're going to get like a sludgy atmosphere, which I'll go through here. So inner planets formed where it was very warm. They tend to be rocky with metallic materials that can condense. It's too warm for gaseous materials to be able to condense into solids. And so as a result here, they have rocky exteriors and metallic cores. They're very dense, but they have very thin atmospheres. Relatively speaking, they're pretty small, and they have another important name. They're called the terrestrial planets. Outer planets formed where it was relatively cold outside the frost line. Gaseous materials are able to condense into solids or ices. So they're very massive, and they're massive enough to be able to hold a lot of gas nearby them because of that gravitational pull, and thus they'll have very thick atmospheres compared to us, which is really not conducive to life. So they're huge in size. I mean, look at the difference in size here. These are our inner planets compared to our outer planets. I mean, there's a reason we call them the gas giants. The planets themselves are not very dense. In fact, if you took Saturn, based on the density we figured out, it could technically float in water, which is really weird. There's no solid planet surface. Really what you can think of it as is slushes and liquids surrounding a tiny, tiny rocky core. So their names again are gas giants, or another name is Jovian planets. Okay, I'm going to skip that for credit recovery. So knowing your inner and outer planets as well as the process of accretion would be critical from this lesson, and I'm going to wrap it up here. You should have one more quiz.